In this presentation, I'm going to go over the types of chemical reactions we'll see in this class, as well as some advanced chemical balancing techniques. So first, we'll go through a quick refresher on what chemical reactions are and how they're structured, and then we'll go through the 5 types of reactions that we will specifically see in this class. So first, that structure of chemical reactions. Remember that on the left side of any chemical equation, that's our starting point. We start with our reactants, and these are basically the starting ingredients for any reaction. We then put a right-facing arrow, and that shows where those reactants are going or what they're becoming. And our final product we put on the right side, and those are our products. This is what is left over after our reaction is complete. An example in, like, say, real life would be if we start with ingredients, our reactants, such as eggs, flour, and sugar. Say we're baking something. If we combine those reactants, they will become a product such as cake. So this is analogous to what we see in chemistry. We take our reactants, we put them together, we give them some kind of heat usually, and they become a product. Now, in this presentation, I want you to start seeing the chemical parts in a couple different ways. It's easier to see how these reactants change if you see them as their pieces. For instance, hydrogen and oxygen are essentially our pieces, and they combine to form H2O. They're combined, but we still want to be able to see them as where they came from. The H's and the O's were distinct pieces. Because we'll see that these switch positions and partners in some of these reactions. Also, we talked about polyatomic ions in a previous section. Notice that NO3, even though it's made of multiple elements, nitrogen and oxygen, it acts like one piece. Even though it's multiple elements, it stays together on both sides of the reaction. Now let's talk about the types of chemical reactions that we'll see. Earlier on, we talked about looking for clues to say that a chemical reaction had occurred, such as flames or light or heat or bubbles or smoke. These were all indications that some kind of new chemical was being formed. However, now that we've talked about elements and reactions, we can start to define what kind of reactions we have. First, we'll talk about synthesis and decomposition reactions. These two sort of go together, they're sort of opposites. We'll talk about combustion reactions. The name kind of gives that away. We're talking about usually fire or light in that case. And then another set of paired reactions are single replacement and our double replacement reactions. Now, these are just a small sampling of all the reactions we'll see. There are also reactions such as acid-base neutralizations, and the farther you go into chemistry, you'll see there are many, many more types of reactions. But for us, these 5, synthesis through double replacement, really get us a long way. First, let's start out with synthesis. Synthesis is pretty simple. We'll see that we have 2 or more reactants combining to form one product. In this case, sodium and chlorine, 2 reactants, combine to form sodium chloride, one product. This is also called a combination reaction because you're simply combining your reactants. Some examples: if we take hydrogen and oxygen, we combine them to form water. We have one product, so therefore it's synthesis. Or if we take iron and sulfur and combine them to form iron sulfide, again, we have 2 reactants forming one product, so that is a synthesis reaction. Really, the clue for this reaction is if you have one product, that is typically a synthesis reaction. And that iron sulfide, I put this up here to show that they don't all look the same. Sometimes synthesis reactions are very bright and let off a lot of heat, but not always. Although I will say that this kind of reaction is sort of common. Now let's take a look at a balancing chemical equations problem with synthesis reactions. Taking a look at this synthesis reaction, we have H2 plus N2 making NH3, that single product. If we do our balancing here, we can see we have 2 H's on the left and 2 N's on the left. We have 1 N on the right, remember a blank means 1, and 3 H's on the right. As a quick reminder, remember that no number in front of these molecules means 1. Blanks are 1. I'm going to leave those out, though, because traditionally we leave 1s out. Now, in this problem, both of our atoms are unbalanced. We have more hydrogens on the right and more nitrogens on the left. So we need to get equal numbers on both sides. It doesn't matter which atom we start with, but I can see it's going to be very easy to balance nitrogen by just giving myself 2 nitrogens on the right side, on the product side. So if I put a 2 in front of this NH3, that's like saying 2 times 1N and 2 times 3 H's. Or in other words, 2 times 1 is 2 nitrogens, and 2 times 3 H's is 6 total hydrogen atoms. Now I can see my nitrogens are balanced at 2 and 2. So let's target my hydrogens. What number times 2 would get us up to that balanced number 6? Well, 3 groups of 2, 3 times 2, gets us up to 6 hydrogens. And now my hydrogens are balanced as well at 6 total on both sides. I could, again, put a 1 here in front of that nitrogen to remind myself I have 1 of it, but I'm going to leave it blank. And this is our balanced equation for this synthesis reaction. Next up, we have decomposition reactions. In these types of reactions, they're sort of the opposite of synthesis reactions. These are when one reactant breaks apart into multiple products. We can see that H2O2, or hydrogen peroxide, is breaking into 2 products, water and oxygen. This is sort of the opposite of a synthesis reaction. In synthesis reactions, we put reactants together. In decomposition reactions, we break reactants apart. 2 examples. If we take silver chloride and form silver and chlorine, we have 2 products from 1 reactant. That is a decomposition, just like copper to carbonate, forming copper oxide and CO2 gas. Again, 1 reactant becoming 2 products. This is a decomposition reaction. Again, let's take a look at an example of balancing a decomposition reaction on the other screen. So here we have our decomposition reaction, H2O2 becoming H2O and O2, 1 reactant becoming 2 products. If I do my initial counts, I have 2 hydrogens and 2 oxygens on the reactant side. On the product side, I have 2 hydrogens, and notice that I need the total number of oxygens on the right side. So I have 1 from this molecule and 2 from this molecule. So in total, I would have 3 oxygens. Now this problem is deceptively difficult. There is no number I can put in front of here to get directly to 3 oxygens. In situations like this, I would recommend simply giving yourself more oxygens on the left, and you'll see that it will naturally balance itself out. Really what's making this difficult is oxygen is in multiple places on the product side. But I'm going to give myself more oxygens over here. I'll just pop this up to a 2. 2 times 2 hydrogens is 4. And 2 times 2 oxygens is 4. So I gave myself more oxygens because it wasn't quite working out. Now it looks like I made this tougher for myself because both elements are now unbalanced. But you'll see that this will naturally balance itself out. If I give myself balanced numbers of hydrogens again, put a 2 in front of here. 2 times 2 hydrogens is 4. Getting myself rebalanced with hydrogen. And the total number of oxygens on the right side, 2 times 1 is 2 from this molecule. 1 times 2 is 2 from this molecule. So in total, 2 plus 2 gives me 4 total oxygens. And you'll see that I am now balanced at 4 oxygens on both sides and 4 hydrogens at both sides. Remember, this problem was difficult because there was no number to get our oxygens immediately balanced. In that case, we simply gave ourselves more oxygens on one side to balance out, and eventually the problem worked itself out naturally. Our third type of reaction is a single replacement reaction. These are a little bit tougher to see. This is when one reactant switches its partner with a different single element. Notice when we're starting with our reactants zinc by itself and hydrogen bonded to chlorine, we're ending with zinc bonded to chlorine and hydrogen by itself. Essentially what happens is the zinc kicks out the hydrogen, forming a new partnership, and the hydrogen is left alone, sort of like these 2 reactants swap positions. This is sometimes called a single displacement reaction, but they're the same thing. A couple examples. If we take sodium and chlorine, the pair, plus silver, the single element, and form silver chloride and sodium by itself, Single replacement because we have one element being switched out in the partnership. Also, silver and sodium nitrate, we have this polyatomic here, forming sodium by itself and silver nitrate because we have the silver essentially replacing the sodium in this partnership. We have a single replacement. The main clue to look for is that on both sides of the reaction, there is a single element. And in both of these cases, you'll see silver by itself on one side and sodium by itself on the other. Now let's take a look at a balancing problem with single replacement. So here we can see we have our single replacement reaction, lithium and magnesium nitrate. Notice the nitrate stays together on both sides of the reaction, becoming lithium nitrate and magnesium. So again, I'm going to count by lithium and magnesium, and I will keep the nitrate groups the same on both sides. I'll count by nitrates instead of splitting this up. I have one lithium to start on this side, one magnesium to start on the reactant side. Looks like I have two nitrate groups on the reactant side. Now on the product side, I have one lithium, one magnesium, and this nitrate, even though it doesn't have the number, it's sort of like saying, since there's no multiple groups, it's sort of like saying you're starting with one nitrate group. And it's not wrong to give yourself that parentheses to remind yourself that this molecule has one nitrate to start. Now, I need to balance the nitrate. That's the only thing not balanced. If I give myself 2 of this molecule, it's like saying 2 times 1 lithium and 2 times 1 nitrate. That gives myself 2 times 1, 2 nitrates, and 2 times 1, 2 lithiums. Now on the left side, all I have to do is give myself 2 times 1 lithiums, pop myself up to 2 lithiums. And now my problem is balanced. 2 lithiums on both sides, 1 magnesium atom on both sides, and 2 nitrate groups on both sides. And that's balancing this single replacement reaction. Next, we have our double replacement. These are very similar to single replacements, except instead of one atom switching with its partner, we have 2 atoms switching their partners, or rather 2 elements switching their partners. In this, we start with zinc fluoride and hydrogen chloride, and we're forming zinc chloride and hydrogen fluoride. Essentially, the zinc and the hydrogen switched their partners. This is also sometimes called a double displacement reaction. 2 more examples of these: sodium chloride and silver bromide, forming silver chloride and sodium bromide. The silver and the sodium switch partners. In our second reaction, silver chloride and sodium nitrate form sodium chloride and silver nitrate. Again, the sodium and the silver switched partners. We'll take a look at a quick balancing problem for these types of reactions. Now, this problem for this double replacement looks difficult, but it's actually not too bad. If I quick color code our groups, notice that NH4 stays together on both sides, so we'll count by NH4s. If I give myself a different highlighter, looks like OH stays together on both sides. So OH is one of our partners in this double replacement. Looks like Cu stays together, or is by itself on both sides, but it's with that partner ion. And Cl is that other partner ion. So we can see NH4 switches places with Cu. Instead of NH4OH, we have NH4Cl. And instead of CuCl, we have CuOH2. And I'm going to count by these polyatomic ions in that balancing down below. So if I'm going to balance, I'm going to start with one of these NH4 groups. And if it helps you, you can always remind yourself that there's no parentheses, you're starting with 1. I could do the same with OH, reminding myself I have one of that OH group. In fact, let me spread out this equation a little bit to make that a little bit nicer and neater for you. Give myself one of these NH4s, and as a reminder, one of these OHs. So I'm starting with one OH as well. On the reactant side, I have one Cu atom and 2 Cls. On the product side, looks like one Cu atom, 2 of those OH groups, one of these NH4 groups, give myself the parentheses as a reminder, and one of these CLs. So for my balancing down below, it looks like Cl is not balanced and OH is not balanced. I'm going to make things easy and just focus on the Cl instead of dealing with the polyatomic. I'll put a 2 in front of here to get 2 times 1 NH4s, so 2 NH4 groups. 2 times 1 Cl, so 2 Cl groups. And now it looks like Cl is good, Cu is good, but my OHs and my NH4s, I have 2 on the right side and only 1 on the left side. But notice, if I put a 2 in front of this molecule right here, 2 NH4 groups, 2 times 1 is 2. 2 OH groups, 2 times 1 is 2. And now I'm balanced. 2 NH4s on both sides, 2 OHs on both sides, 1 Cu on both sides, and 2 Cls on both sides. And our final type of reaction, our combustion. In this type of reaction, we have a fuel source, such as CH4, combining with oxygen by itself to form CO2 and H2O. The combustion reactions are always when oxygen is by itself as one of the reactants. Oxygen is what causes a combustion reaction. Usually, but not always, we have 2 products, CO2 and H2O. Also, usually light and heat, because combustion reactions, you can think of them as creating fire in some source. Now, combustion reactions. We're going to break this down with 2 typical examples, such as C8H18 combining with O2 to form, again, CO2 and H2O. The clue here, O2 is by itself, and this is octane. This is what you'll see in like a gas combustion engine. We also have C3H9O. This is isopropyl alcohol, combining with, again, O2 by itself to form CO2 and H2O. These are both combustion reactions because O2 is by itself as a reactant. These 2 are slightly different reactions. They're still combustion because O2 is by itself as a reactant, but notice that the products are not CO2 and H2O. You can still combust with these metals, say zinc and iron, but it doesn't give you the same product. You don't need CO2 and H2O as your products. You can create these metal oxides in combustion reactions as well. Notice that in these reactions, these are also synthesis reactions. In both of these cases, we have 2 reactants to forming 1 product. So these fall under 2 categories, combustion and synthesis. Now, combustion reactions can be a little bit difficult to balance, and we'll see that on the next slide. Now, combustion reactions, remember this O2 on the reactant side shows that it's a combustion reaction. Combustion reactions can be sometimes easy and sometimes difficult to balance. I'll start with an easy one and then show you the more difficult one. On the reactant side, we have 3 C's, 8 H's, and 2 O's. On the product side, we have 1 C, 2 H's, and in total, looks like 2 over here, 1 from here. In total, we have 3 oxygens on the product side at this point. So this problem, nothing is balanced, but my only recommendation here, and I'll write this in a different color on the right side, is to save oxygen for last. In fact, this isn't a bad option for any balancing chemical equation problem. Oxygen is oftentimes all over the place in these equations. And it's often by itself, especially in combustion reactions. So we usually want to save oxygen for last. So if I head back over to my problem, I'm going to do carbon first. I need 3 carbons on the product side to balance, so I'll put a 3 in front of my CO2. 3 times 1 carbon is 3 carbons. It does change the oxygens, though. 3 times 2 gives me 6 oxygens. And from this molecule, 1 times 1 is just 1. So in total, 6 and 1 gives us 7 total oxygens. Now we need to work on hydrogen next. We're going to save oxygen for last. A 4 in front of this molecule, 4 times 2 hydrogens, gets us up to that 8 that we need. 4 times 1 oxygen, well, that's 4, but don't forget, we still have 6 from this molecule. So 6 and 4 gets us up to a total of, 10 oxygens. And now this problem's only one step away. Because we saved oxygen for last, what number times 2 gets us up to the 10 we need? Well, 5 times 2 gets us those 10 oxygens. So this reaction balanced itself pretty well. 3 carbons on both sides, 8 hydrogens on both sides, 10 oxygens on both sides. This equation, not too bad, just acts like a normal problem as long as we save oxygen for last. However, this problem is a slightly more difficult problem. I'm again going to remind myself to save oxygen for last, and I'll do my initial count. 2 carbons, 6 hydrogens, and 2 oxygens on the left, 1 carbon, 2 hydrogens, and in total, 2 and 1, in total, 3 oxygens. Again, we're going to save oxygen for last. I'll do carbon first. 2 times 1 gives me 2. Oxygens, we have 4 here and 1 here. So in total, 5 oxygens. I'll do hydrogen next. 3 times 2 gives me that 6 that I need. But again, it's going to update our oxygens. 4 from here, 3 from here. So in total, we have 7 oxygens. So now we're in a weird situation where oxygen, no number in front of that oxygen, gets us up to the required 7. What we can do instead is take all of these coefficients, 1, 1, 2, 3, and simply double them. What this will do is it will help us get a number in front of that oxygen that works. But for now, I'm just going to double all of those coefficients. I'll erase the ones we had. And I'll move down these new doubled coefficients. And we'll see that our updated counts work out nicely. 2 times 2 is 4 carbons. 2 times 6 is 12 hydrogens. 2 times 2 is 4 oxygens. 4 times 1 is 4 carbons on this side. 6 times 2 is 12 hydrogens. And in total, 4 times 2 is 8 oxygens from this molecule. 6 times 1 is 6 from this molecule. 8 plus 6 in total gives us 14 oxygens. Now we do have a number we can update this oxygen to get us 14. Instead of using the 2 here, what times 2 gives us 14? Well, if I use a 7 instead, 7 times 2 gets us that 14 that we need. This doubling of all the coefficients gets us out of that situation. We also talked about a method in class using decimals. Either way will work. One just is more helpful if you're comfortable with decimals. And this is how you would get through a more difficult combustion balancing problem.